Okay, pre-calc people, here we go. This is part 2 of the dot product notes focusing on scalar and vector projections. It's sort of an application in physics where you are calculating the force it takes to, say, pull an object, how much energy is going into moving the object horizontally versus how much energy is being wasted or assumed by the vertical motion if you're pulling something. So we're going to focus on the mathematics because my physics is kind of weak. But let's start off with talking about what is a scalar projection. So you start off, we have this vector A. And we have this vector B down here. It goes all the way out to here. All right. What we're going to look at is a scalar projection as if the sun were shining down on A, of how it then leaves a shadow on B. That would be called a scalar projection. So initially I'm just going to call that P, no little arrow over it. And basically we have a right triangle here. We are just doing right triangle trig because we know that the cosine of theta is the adjacent, which we're going to call P, over the hypotenuse, which would be the magnitude of A. And I can then isolate my adjacent side by multiplying the magnitude of A to the other side. That is called the scalar projection of A onto B. If the theta here is acute, then the scalar projection will equal P, but if the theta happened to be, I don't have a lot of room here, but I'll draw a little vector. If this happened to be our theta and it happened to be obtuse, then notice that my scalar projection coming down right here would actually be the opposite of P. And when later on when we turn that into a vector, it's a vector then just going in the opposite direction. Okay, which makes sense because cosine of an obtuse angle would be negative. So what we're going to be finding is the length of this adjacent side. That's what we're calling a scalar projection. And since it's falling onto vector V, we call it a scalar projection of A onto B. Okay, so the first thing we're going to do is see that this comes to you in many forms, and it really depends on how the information comes to you. And you can either use the new revisions of what the formula is, or you can start from scratch and just go through the same derivations that we're about to do. So let's start off with this. So we know that it's a scalar projection because remember, you're just finding the length of the adjacent side. That was A cosine theta. And what we're going to do is a fancy little trick here. We're going to multiply by 1. The form of 1, though, is going to be the magnitude of B, the vector we're projecting onto, over the magnitude of B. So that's just the same thing as 1. So hopefully that's okay so far. So what I can do is simplify this, though. Hopefully you recognize now in the numerator, I can rearrange that. I've got the magnitude of A times the magnitude of B times cosine theta all over the magnitude of B. And we can simplify that because we know the numerator there, when you have the magnitude of A times the magnitude of B of cosine theta, an easier way of saying that is A dot B. So that's your dot product over the magnitude of B. That's a really nice form to use if everything comes to you as its component parts, because it's easy to find the magnitude. The dot product or inner product is really easy to find. We know the dot product is a scalar, magnitude is a scalar, so it's still a scalar projection. Okay, so hopefully that is okay. So then sometimes we don't want just the scalar, we want to find what that is as a vector so that it has the direction and the magnitude. So what we're going to do with this is we are going to take that scalar projection and we're going to multiply it by a unit vector. Remember that has a magnitude of 1, so it's not going to change the length of my scalar, but it will make it go in the b direction if I multiply by the unit vector of vector b. Okay, so it's just going to take our scalar and turn it into a vector without changing its magnitude and keeping the direction in the direction of b. So the way this is going to work is we are going to take, I'm not sure why I have, so this is basically what it would look like. This initial part, remember, here's our adjacent times the hypotenuse times the cosine of theta multiplied by our unit vector, okay? And what we just saw above was that if I were to rewrite, we know that this, from what we just did, cosine theta, can also be transformed into the dot product over the magnitude of b. Again, that's still a scalar. We want to turn that into a vector. So we're going to multiply that by the unit vector. So that's going to be b over the magnitude of b. And what that does is it simplifies it. So we have a dot b over the magnitude of b squared. That right there is still a scalar. It's just a all number. Dot product's a number, magnitude's a number, but we are multiplying it by the vector b. That's the part that turns it into a vector without changing anything about it, because it's a unit vector that we multiplied by. It maintains the same scalar length. All right, so what I just did was I showed this part right here. So this will be one of the formulas we might want to use. If we're just finding a scalar, we might want to just use this one. And again, both of these we just derived. So you could also go back to, if you can find the magnitude and theta, you can go through this same process. All right, so let's see how this works out. So we have an example here. B is 8, negative 5, 3. So I'm just going to draw a vector here. I'm not going to draw it in its real x, y, z components. So here is vector B, 8, negative 5, 3. And vector A, we happen to know has a magnitude of 10, and the angle between them is 70. So we're going to initially drop our shadow here and find our scalar projection. Since they gave us the magnitude, they gave us the degrees, this is really just right triangle trig. The scalar projection is just going to be 10 cosine 70 degrees, which is going to be 3.42. Okay? And that's it. That's all you have to your scalar projection, if you're given the magnitude and the theta. To turn it into a vector projection, I'm going to multiply that 3.42, I'm going to multiply it by a unit vector of b. So let's first find, we're going to need the magnitude of b. So b is going to be 8 squared, so that's 64, plus 25, plus 9. And let's see, that is going to give us 98, so 49 times 2, so 7 root 2. So to turn our p into a vector now, so now it gets a little arrow over it, we're going to take our 3.42 and we're going to multiply it by the vector 8, negative 5, 3, but we're multiplying by the unit vector, which means it's getting divided by the magnitude here. And so what you would usually do is then just go to your calculator and get a nice decimal for all of this. So we should get 2.76, negative 1.73, and 1.04. So this would be our vector projection. So one of them is a scalar, and then by multiplying by the unit vector, of the vector you're projecting onto, you turn that scalar projection into a vector projection. Okay? So it's nice if you're given, you know, the magnitude of that vector and you're given the angle between them, but that doesn't always happen. So what we want to see is what happens when it comes to you in other parts. So as I was saying, you're given, so we're given it in our component parts. So you have options. You could go back to the beginning, figure out the scalar, figure out the magnitude of this separately. We've already looked at in the other video how to find the angle between them. But we also have shown how you can kind of derive another formula to find that projection. So we have R right here is being projected onto S, and we have both of them in component form. And so we know that if we're going to do the, I'm going to call this P right here, this is going to be our scalar projection. So I'm going to go back and use what we derived is the dot product over the magnitude of B, because again, that's all a scalar. That will give me the scalar projection. So, because remember, A dot B is magnitude of A times the magnitude of B times the cosine of the angle, without having to know what that angle is. So let's go ahead and calculate this out. So the dot product is going to be on top. We have 1 times 5 plus 4 times negative 2, so negative 8, plus 21, all over the magnitude of, I did it again. I should have written R and S and P. I'm sorry about that. Oi, oi, oi. So this is R. Let me see. I think I have an eraser here somewhere. Is that an eraser? It is an eraser. There we go. Okay. Go back to my pen. So this is R dotted with S all over the magnitude of S. There we go. Okay, the magnitude of S we are going to have to find. So the magnitude of S is going to be 25 plus 4 plus 9. And then working that all out, that gives us 18 over the square root of 38. That is our scalar projection. Okay? And again, that's the shortcut way of doing it. You could go back and find the magnitude of R. You can use your dot product, rearrange the magnitude of R times the magnitude of S times the cosine of theta to find the theta between them. But that's what our derivation allowed us to do a shortcut. Okay? Now, we want to turn this into a vector. So how do you turn it into a vector? You multiply by the unit vector of the one that is being projected onto. So that means I'm going to take we're going to take P, it's going to become a vector now. We take the scalar projection, which was right here, square root of 38. We're now utilizing the formula, if you want to put it that way, which was our A dot B over the magnitude of B now gets squared times the vector B, because we're turning it into a vector. And of course we're doing it in terms of R and S. So that means we have our dot product, we've already got that. We already have the scalar 1, so all I'm going to do now is square that and multiply it by the vector B, which is, in this case, is S. So this will be 5, negative 2, negative 3. So 18 over 38, which is equivalent to 9 over 19. So 9 over 19 is getting multiplied through by 5, negative 2, negative 3. And that's just going to give me, I'm going to leave it in fractional form. So I have 45 over 19. I have negative 18 over 19. And I have negative 27 over 19. And that is a vector. So that is turning our P into a vector projection. Okay, I hope this made sense. It's a little hard in a video. There's some things I'd like to say and I'll probably expand on in the class, but hopefully at least you kind of got the basics.